Welcome to the Runge-Kutta method. So the idea here is we want a numerical approximation technique. Which has smaller error, right? So which results in an even smaller error. So we're essentially going to build on the improved Euler's method. So recall Euler's method the linear approximation we were working with was based off of 1-point slope. So each linear approximation was based off the slope at 1 point. Improved Euler's method we used 2 points. And for Runge-Kutta, we're actually going to use 4 points. So I'm going to sort of show how we find those 4 points visually first, and then we'll get to the more precise formulas. So visually, we have our point xi, yi at our ith stage of the algorithm. We find the slope at that point. Then we have, here's our step size, h. We are going to start by only going out half of that. So we'll start by taking this line and only going out h/2. So we're going to go a half step. Or h/2. And we find our new point just following the tangent line from that point. Now we're going to find this new slope. And we're going to take that slope back to xi, yi and find the line with that slope. So here's our first point. Right. Then our second point. Our first point will have y prime, we'll just call it k1i. It's the first point we're finding a slope for the ith iteration. At 2, we'll have y prime is labeled to be k2i, our second point slope in our ith iteration. Then we have our third point, which was also halfway through. This one will have slope y prime is equal to k3i. And then we will use that slope to create a line. And this time around, we'll go the entire step. And once again, we'll find the slope here. So this is our point 4. Now it has y prime is equal to k 4I. So we essentially keep, every time we create our line, we go back to the initial point for that step, but the slopes are coming from each of these points we're finding. So we have 4 different slopes we've found, and the actual line we will use for our approximation. So the line to be used for the approximation will have slope, or will have point xi, yi, and slope, which I'll call ki, which will be 1/6 times the slope of the first point, k1i, plus 2 copies of the slope of the second point, plus 2 copies of the slope of the third point, plus the slope at the fourth point. What this is the average of the consecutive averages. So this is essentially if we averaged the slope from 1 and 2, averaged the slopes from 2 and 3, and then averaged the slopes from 3 and 4, and then we took the average of those 3 averages, this is what we would get. And so we have the equation will be y is approximately yi plus our step size. Well, we'll start off with our slope ki times x minus xi. And we have our yi plus 1 is therefore considered to be yi plus k times our step size, so kh, or yi plus k times xi plus 1 minus xi, right? They're equivalent. So in our algorithm, this is the final equation we'll get for the y values we're using. Along the path, we will have sort of modified points that we'll be using. So again, the algorithm for our various k's. So we start with xi, yi. Find y prime equals f of xi, yi. And this we will call, this is our k 1i. Here we find the line through xi, yi with slope k1i. So that was our initial purple line we drew. using that line, find the y value at xi plus h over 2. And we'll call that y value, I'm going to call the x value, sorry. We'll call the x value x2i because we're at the second point. And call the y value y2i. From here, now we'll find the slope at x2i, y2i. So this will be y prime is f of x2i, y2i. And we will call that k2i. There's our second slope. Then we will find the equation or find the line through point xi, yi with slope k2i. Using that equation, find the y value, which we will label y3i at x value x3i, which again will be xi plus h over 2. Once again, we will find the slope. So we'll find the slope at x3i, y3i. And that'll be y prime is equal to f of x3i, y3i, and we will call it k3i. Now we're going to do one more equation. So we'll find the equation for the line through point xi, yi. With slope k sub 3i. And we will use that line to find the y value y4i at x4i, which is just x sub I plus 1, also known as xi plus our step h. Here we find one more slope. So we'll find the slope at x4i, y4i. Again, this will be y prime is equal to f of x4i, y4i, which we will call k4i. And now we will find the sort of average slope. I'm just going to call it average in quotes slope, which will be k is equal to 1/6 times k1i plus 2 copies of k2i plus 2 copies of k3i plus k4i. So again, that's that slope we were talking about before. Each of my x1i, x2i, x3i, x4i, those are our points 1, 2, 3, 4. And the slopes are the slopes, precise slopes that I was pointing out before. So this is just sort of out in words what the pictures were designating. Now, the linear approximation used for Runge-Kutta is y is approximately equal to yi plus k times x minus xi. And again, we get yi plus 1 is approximately, or is therefore set to be equal to yi plus this k times h, since we're plugging in xi plus 1, and that is precisely h away from xi. So this is what we'll be using in our Excel spreadsheet. I have the spreadsheet set, so we just have to type in the slope formulas and our initial point and our step and the linear approximation formula, and then we're set to go, and Excel will do the rest for you. So in the next video, we'll see how to use the Excel spreadsheet I created for Runge-Kutta.